In this lecture, lecture 12, we're going to start talking about the Rao Blackwell Theorem, which hopefully we'll get to by the end of this course, of the course, hopefully, by the end of this lecture, definitely. Scratch that, reverse it. But so we're going to continue talking about best estimators for a couple more lectures before we get into convergence of these estimators or asymptotic properties. But we had seen in previous lectures, we had seen that in certain cases, most notably for exponential family random variables, that we could get a best estimator for a parameter. And we could get that using the Cramer-Rao lower bound. We could show that Cramer-Rao lower bound was attained in certain cases, and therefore we got the best estimator. But there are some cases where that approach won't work. Notably, non-exponential families, we can't use the Cramer-Rao lower bound because the family of distributions doesn't have the nice regularity properties that allow us to use that bound to find the best estimator. And so what we're going to talk about probably for this lecture and the next one is what do we do in these other cases? We don't have an exponential family. Or is there another way of finding best estimators? So that's going to be the topic that we start getting into today, and that will lead through the Rao Blackwell Theorem, which we will hopefully touch on today, and next time we'll talk about the Lema-Schiffe Theorem, which really it's the kind of crowning achievement of this area of mathematical statistics. And this is stuff that was proven about around exactly 1950 or so. So we're up to 1950 in our knowledge of this stuff. So we're going to do a little bit of a review of iterated expectation at the beginning of this. And we talked about this a little bit last time. And the reason that we're going to do this review is that the Rao Blackwell Theorem and the subsequent Lema-Schiffe Theorem rely on conditional expectation. And so conditional expectation is something that's covered in 451, but may be a little bit rusty. And if you're rusty on it, it's going to be a little bit hard to follow. So it's worth going over this. We talked about it a little last time, so I won't get too much into the details. The most important theorem is, of course, the iterated expectation theorem. So let's write that out. And the iterated expectation theorem says that if I want to calculate the expected value of some random variable x, and x is jointly distributed with some other random variable y, I can instead calculate this as the expected value of x given y. So we talked a little bit last time about what the meaning of the expected value of x given y is. And we also note that this first expectation is with respect to x, and this outer expectation, you could put a little subscript y, is kind of, quote, with respect to y. So what do I mean? When we calculate, say, the expected value of a random variable x, if it's continuous, for example, it's x times f of x dx. So we calculate that interval. And you could even say, although it's a little weird to say, but you could put a little subscript x to mean that we're calculating with respect, we're calculating against or multiplying against the PDF of x, fx. And I could, if this were the PDF of y, you could say the expected value of, against the PDF of y which is what we're doing in the outside here of whatever, it would be whatever times f of y dy. So when I write this little subscript, the first, we could even say, let me say, just back up here, we could even say with respect to x given y of whatever, which would be the integral of whatever against x given y, the conditional PDF. This would be dx because the x is the first one here. So basically, what I mean is that this first integral is with respect to x, so we're integrating against fx. This inner one is with respect to x given y, that's the conditional expectation, and this outer integral is with respect to y. So I guess I should say this is respect to x given y, and this outer one is respect to y. So first one we integrate against x, this inner one we integrate against x given y, and this outer one we integrate against y. So it's just good to keep that all in mind. But the theorem says that if I just knew the conditional distribution of x given y, and I knew something about the marginal distribution of y, I could calculate the expected value of x. We could even do a proof of this. It's not so bad. Basically just some rearrangement here. We should first note that our definition of the conditional distribution x given y is fxy over fy, and equivalently, the conditional distribution of y given x is the joint over the conditional of x. So we can write this joint, if I move this fy over and we move this fx over, we get that the joint of x and y is either x given y times f of y, or the second one, if I move fx over, it's y given x by fx. So you can think of that joint as an either way there. So that's just an aside fact. We want to prove the theorem, and you can take it from either side. You can either take the left side and show it's equal to the right, or the right side and show it's equal to the left. Let's first look at the expected value of x. And the theorem's not so bad, and it's good to understand the proof in so much as that you actually understand what the theorem's really saying, if you can understand this proof. So the expected value of x is, in just the continuous case, let's just say continuous. Same thing with discrete, but integrals are kind of nicer to work with. You just replace the integral with the sum in the discrete case, but in the continuous case, expected value of x is the integral x fx dx. And fx, we know we can write this as the integral of the joint over y. So this thing is equivalent to fx, right? If I want the marginal of x, I take the joint and I integrate out y. And let's just pull both our integrals out. And so we have x by the joint dy dx, oops, not dy dy, dy dx. And we can now use our fact, one of our two versions of this fact, which do we want? Well, ultimately we want it in terms of y given x, so let's, yeah, so I think that's probably the way to do it. Let's see if we can do this on the fly. This is x against f of, I'm sorry, we want it in terms of x given y, that's f of y, right? That's the same thing as that joint. And let's say dx dy. So let's just switch the order of those two. That's not too bad. And so this inner integral depends on x. And so anything depending on y we can bring outside to the outer integral. So this is the integral of x by fx given y dx. That's my inner one. And then on the outside we integrate we can pull out my f of y dy. And this is, we could call that the expected value of x given y is whatever little y is, times f of y dy. And that, this whole integral, is what we call the expected value of x given y. And so if that last jump is confusing, you should go back to the end of last lecture where I talk about what is this notation x bar y, where both x and y are capital, mean, right? The real shorthand notation is that, you know, the expected value of x given y as some little y is some function that depends on what little y is. So I change little y, I get a different value. And so the expected value of x given capital Y is just, we just treat whatever this y is in this function, instead of as being a little y, we just say, well, let's just treat it as if it were random. And that's just purely notation. But so this thing is basically g of y, and so this thing is capital G of y. And certainly that the, you know, if I integrate some g of y against f of y dy, that would be the expected value of g of y. And that's the theorem. And so you notice that this first integral was against x, so with respect to x. The inner one is against f of x given y, and the outer one is with respect to y. So that's what I mean. It's good to go through that proof and understand that proof, because then you really understand the different moving parts in this theorem. Otherwise, this theorem can be a little bit intimidating. So that's the theorem of iterated expectation, or also called the theorem of total expectation. And there's a follow-up theorem called the law of total variance, or the total variance theorem, or the iterated variance theorem. And it is a very similar theorem, but instead of looking at the expected value of x, we can look at the variance of x. And here it is the expected value of the variance of x given y plus the variance of the expected value of x given y. Oh, let's write that legibly here. We can put some brackets around it to make it a little more clear. So the way to remember this is that it's the expected value of the variance plus the variance of the expected value. So you kind of switch those roles. And we talked about this last time, expected value of x given y is a random variable. And in the same way, variance of x given capital Y is also a random variable. So if variance of x bar y is a random variable, it has an expectation. And if expectation of x bar capital Y is a random variable, it has a variance. So everything in here makes sense. These are both random variables, so different random variables. But they're pretty easy, right? And we'll see in the examples. The notation is much more complicated than the theorem actually is, because all we're doing is calculating this conditional variance or this conditional expectation, and then replacing the little y's with the capital random variable y's. I won't do a proof of it. It's pretty much, you can bootstrap the proof off of the previous theorem. But let's look at some examples just to refresh people's memory with this stuff. So my example here is that x given y is some value, little y. So if I knew what if I knew what capital Y was, it's some value, little y. Let's assume that x is binomially distributed with the number of trials, which is usually denoted by n, but that's going to be little y, and the probability p is just some number, so p is just some probability, some number between 0 and 1. but y is Poisson distributed with some rate parameter lambda that's positive. So the way to think about this is what's my experiment here? First, I'm going to generate some y. I'm going to randomly sample from a Poisson distribution. Now, Poisson is a count, 0, 1, 2, 3, etc. Right? So I'm going to generate a number, an integer, a non-negative integer, y. And then once I have that y in hand, so that realization, what I call little y, I'm going to generate a binomial random variable where the number of trials in my binomial random variable is whatever the y I've realized. So I generate y, and then given, maybe y is 5, given 5, I'm going to generate a binomial 5 with some probability p. So these are what might be called hierarchical models, or a simple version of a hierarchical model. And what do I want to know? Maybe I want to say, what is the expected value of x? So the situation is I randomly generate a number of trials, and then with that randomly generated number of trials, I generate a binomial. I randomly generate a number, and I flip a coin, a weighted coin, that many times. How many heads do I expect to come up? For example, that's a really simple example here. And if I do this procedure a bunch of times where I generate the number of trials and then I generate coin flips or the binomial from that, what do I expect my expected value to be? We might expect it's not, I don't know what we expect. We expect the expected value to be because there's some added randomness because the number of trials itself is random. It's not just we do 5 coin flips, we generate. One time we do 5 coin flips, one time we do 10 coin flips, one time we do 3 coin flips, right? So we're generating the actual number of coin flips randomly too. Luckily, our iterated expectation comes in handy here because we have a theorem here that says if I want to calculate the expected value of x, I can calculate the expected value of first x given y, and then I can take that thing and calculate its expected value, and that will give me the overall expected value of y. So if I know conditional and the marginal of y, I can get the marginal expectation of x. So we have a couple steps here. First of all, we need let us generate the expected value of x given y is some little y. So that just uses the first distribution. X given y is little y is binomial yp. What's the expected value? So this thing is binomial yp. What is the expected value of a binomial? It's just the product of its two parameters. So it's y times p. And now I need to form this object, this expected value of x given capital Y. And all this is I replace my little y here with a capital Y. So while notationally it's kind of very weird, that's all I'm doing. I'm replacing my little y with my capital Y. And now this thing is a random variable. Clearly it's a random variable. It's just p times whatever y is. And my third step then is if I want to calculate the expected value of x, I take the expected value of this e of x bar y. All right, but the expected value of x bar y is just the expected value of y by p. P is a constant, so that comes out. So it's just p times the expected value of y, and y has a marginally a Poisson distribution. The expected value for Poisson is lambda, so this just then gives me p times lambda. And so that's actually pretty interpretable, which is the expected value of kind of heads of my coin flips would be on average how many lambda, which is on average how many flips am I going to do, and p, which is kind of the probability of getting a heads. We could also ask, for example, what's the variance of x? And we have that a little more complicated theorem, that law of total variance, which is the variance of the expected value plus the expected value of the variance. And I think I wrote this backwards to how I wrote it before, but it doesn't really matter. Addition is commutative. So this involves a little bit more work. One, we already know that the expected value of y bar x is just y times p. And so the variance of the expected value of y bar x is just the variance of yp, which is, well, the p can come out, but you have to square it. It's p squared times the variance of y. And y is a Poisson, so actually the variance of y is also lambda. For the other half, so that's kind of this first half here, for my other half here, we need to calculate, whoops. I wrote this all backwards, didn't I? I flipped my variables x and y. Uh-oh. Someone's probably complaining already. This should be x bar y, x bar y. Okay, now we're good. This, though, these also, I wrote these backwards, didn't I? Right? It's x bar y, x bar y. Okay, now that makes more sense. So first we need the variance of x given y is little y. So let's call that step 1. And again, x, just like in this case, x given y is little y is a binomial yp. So now instead of the expectation, we need the variance. The variance of a binomial yp is yp by 1 minus p. And so the variance of x bar capital Y, all we do is we take this formula and we replace little y with capital Y. So we get capital Y, p by 1 minus p. And then the third step is we want the expected value of this thing, which is the expected value of y, capital Y, p by 1 minus p, which is p by 1 minus p and times the expected value of y. And of course, the expected value of y is lambda. So all together, we've gotten our first part here, and we've got our second part here. And our theorem says we've got to add these together, right? So we've got to just add these together. The variance of x is p squared lambda plus p minus p by 1 minus p lambda. We actually get a nice simplification here. It's also just p squared. Surely this simplifies. P squared plus p lambda minus p squared lambda. Yeah, so just p lambda. So that actually works out quite nicely again. And so same variance. The variance is just actually kind of interesting there. And so that's a nice example of conditional expectation. So let's get back to math stats, because that's kind of a probability review. And so what was our problem again? The Kramer-Rao lower bound doesn't always work. And in particular, for non-exponential families, the Kramer-Rao lower bound is not applicable at all. And so what we want is a more general way. A more general method for finding the UMBUE. And what we're going to do is we're going to talk about how we can basically take a bad estimator and make it better. And if we do this carefully, we can take a bad estimator and make it the best estimator. So we're basically going to refine our estimators. Okay. So let's talk about some facts. Now that I've done a review of iterated expectation, let's just use iterated expectation. So here's our fact. We're going to let, what do we want to call it? What do we want to call it? T? Do we want to call it theta hat? Let us have, oh boy, I guess I've been calling it theta hat, right? Let theta hat be unbiased for some function of our parameter, tau of theta, right? And what that means, as we've seen before, is that just the expected value of theta hat is not necessarily theta, but might be some function of our theta, some tau of theta. And let W, which is shorthand for W of X, be some function of our random sample, X tilde. And we'll note here that this is not necessarily, we don't necessarily need a statistic. What I mean by that is W could depend on theta, or unknown parameter, right? So statistics, we insist they don't depend on any unknown parameter. But this is maybe just a quantity. It's just some function of our random sample. And let us define what we're going to call phi of W to be the expected value of theta hat given W. Okay, so here is our conditional expectation, and so you might imagine we're going to use our iterated expectation in here at some point. So just as a reminder, right, W, this depends on my random sample. And I'm calling this thing phi of W because if I give you a different W, I'll get a different conditional expectation. But in the same way that we go back all the way up to this example, right? If I looked at, say, the expected value of X given Y, that depended, X bar capital Y, that depended on capital Y. So if I look at the expected value of theta hat given W, that depends on capital W. It doesn't depend on theta because we've basically gotten rid of that through expectation, but this whole thing depends on W. In the same way that expected value of X bar capital Y depends on capital Y. And so this is my phi. You call it phi of W, or you could even just call it phi, depending on how lazy you are. But it depends on W, which ultimately depends on X. Notice that the expected value of phi is the expected value of theta hat given W. What do we know about that? Our iterated expectation, so this is the expected value with respect to W, let's say. Our iterated expectation formula says that this is the expected value of theta hat, right? That's exactly what the iterated expectation formula says. And if theta hat is unbiased for tau of theta, then the expected value of theta hat is tau of theta. And so what we've shown is that the expected value of phi is also the expected value of tau of theta. So what we've done is we've taken theta hat and something else, and we've used it to create a third thing, phi, whose expectation is also tau. Notice here that if phi is a statistic, then it is an unbiased estimator of tau. Now, if is important. We don't know that this phi doesn't in some subtle way depend on, its formula depend on theta. We didn't insist that W didn't depend on theta. It's possible W is, we didn't insist that W is a statistic, that it doesn't have involved in its formula theta. And we don't know, when we do this procedure conditioning on W, we don't know if phi might also in its formula, if you actually calculate this thing out, right? So like above, we had like speculative x given y is y by p, right? So this thing would not be it's not independent of p in this case. It depends on p, so it would not be an estimator of p. It's not a statistic as far as p is concerned. And so we don't know that phi doesn't depend on theta, and actually in some cases it will. But if it doesn't, if we happen to pick a W well, we know theta doesn't, and depending on W, it could depend on theta or it could not. And if we pick it well, this phi will be another statistic, and it'll be an unbiased estimator of tau also. So that is to say that this process of taking an estimator, conditioning on looking at its expectation conditional on something else, to form this new thing, phi, gives us something that is at least a quantity that's unbiased for, or an expectation is tau. And if we're lucky enough, that quantity will be a statistic and also unbiased for tau. Okay, cool. Here's our fact 2. If we can look at the variance of phi. And the variance of phi, of course, phi is the expected value of theta hat given W. Now, our law of total variance said what? It said that the variance of theta hat is the variance of the expected value of theta hat given W plus the expected value of the variance of theta hat given W. And so we could rearrange. We have part of that theorem. We have this variance of the expected value. So the variance of the expected value of theta hat given W by our law of total variance is the variance of theta hat minus, let me write this in blue just to give the colors, right? So what this says is that if I rearrange the variance of the expected value of theta hat given W, which of course is our variance of phi, is we just move this part over to this side, we subtract it off, right? It's the variance of theta hat minus the expected value of the variance of theta hat given W. Now, I'm not sure that helps us, right? Why does that help us? Well, we want to know something about the variance of phi, of this thing we've created. This potentially a statistic, potentially an unbiased estimator of the quantity we're interested in. And what it is the variance of this quantity phi. The punchline is that this thing is going to be a better estimator, hopefully. And so we want to know something about the variance of it. It's basically the variance of theta hat minus something positive. Right? So the variance, whatever this quantity is here at the end, it's a positive quantity. because the variance is a positive quantity and the expected value of a variance is also going to be positive. So the punchline is that the variance of phi is less than or equal to the variance of theta hat, because it's the variance of theta hat minus something. So surely that means the variance of phi is less than or equal to it. So what have we shown? Basically, we've created a new quantity. I'm not necessarily sure it's a statistic, and will always be, by taking my original statistic and looking at its conditional expectation based on some other quantity. And this other quantity, we have basically no restrictions on it. It just somehow involves our data. If I create a new quantity, that is the conditional expectation of theta hat given W, this thing phi also has an expectation, the same expectation as theta hat, and the variance of this thing is less than the variance of theta hat. So let me just write this out. Summary is that theta hat is unbiased statistic or estimator tau theta. 2, W is some quantity, basically some function of our data. If I let phi be what I get when I look at what I would expect to see in theta hat given W, so if I knew W, what would I expect theta hat to be? Then what we've just shown in our two facts is that 1, phi has same expectation as theta hat, and 2, the variance of this thing is less than or equal to the variance of theta hat. So the implication is that if phi is a statistic, and what I mean by that is the formula for phi is independent, or let me say doesn't depend on my unknown parameter theta, then phi is a better estimator than theta hat. I have basically refined theta hat. So I've taken theta hat, which is just some unbiased estimator. You don't know if it's a good estimator or it's a bad estimator. And I have, through this clever process of looking at the conditional expectation of theta hat given this other quantity W, I have refined it to be an estimator that is no worse than theta hat. So I'm always going to get something that's not worse. I don't know if it's better, but it's definitely not going to be worse. Now, this all really relies on the fact that phi is a statistic. If it's not a statistic, it doesn't really matter. It's not that interesting because you can't really use it. You can't use something whose formula depends on an unknown parameter to estimate the unknown parameter. You can't calculate it if you don't know the unknown parameter. But this implication, I think, really points out where we're going here, which is that in certain cases, we're going to be able to show that phi is a statistic. And so we have basically refined our theta hat. And if you do this in clever ways, or enough, you can refine your way to the best estimator. And that's called the Rao Blackwell Theorem, or Rao Blackwellization. Let's look at an example to make this all a lot more concrete. It's really a bit abstract, or seemingly, because this quantity, phi, just takes a lot to wrap your brain around. What it is basically is, if I have some other quantity W, and I know what that quantity is, what would I expect phi to be? Or, I'm sorry, what? If I have, scratch that. If I have some quantity W, I know what that quantity is, what would I expect theta hat to be? And So it's a bit obscure, but it turns out it has some nice properties, because basically you see that doing that is a refinement of the original estimator, theta hat. So here, let's pick our favorite example. Let us have some data that comes from a normal distribution. Let's just call it mean theta for fun, and we don't really care about the variance. Let's just say the variance is 1. And what we're going to do is we're going to define, let's say, theta hat to be 1/2 times x1 plus x2. So it's basically the mean of x1 and x2. Now we have some capital N x's, and we're only going to use 2 of them to form theta hat. So theta hat's probably not the best we can do, because we're only using 2 data points out of all of our data points. We could probably use better if we used everything. In fact, we know in this case the best estimator is x bar, involving all capital N of our data points. So we know a priori that this thing's not the best we can do. Nonetheless, we can notice that the expected value of theta hat is 1/2 the expected value of x1 plus 1/2 the expected value of x2, which is theta. So theta hat is unbiased for theta. Cool. Probably not the best estimator, but at least it's unbiased for it. We'll show that we can refine it to get a better estimator. The variance of this thing is going to be 1/4 times the variance of x1 plus 1/4 times the variance of x2. The variance of x1 and x2 are 1, and so this just becomes 1/2. So theta hat is unbiased for theta, and it has a variance of 1/2. Not the best estimator, and we could refine it. One way we could refine it is we're going to define a w, and let w be just x1. When I talked about that, our kind of 2 facts above, I didn't make any requirements on w. In fact, w could depend on theta. Even if it doesn't, well, let's see, are we going to get phi to be something useful? If we define w to be x1, we can define phi to be our refinement of theta hat given w. And by refinement, I mean we're going to look at the conditional expectation of theta hat given w. So what is this? Concretely, it is theta hat is 1/2 x1 plus x2, and w is x1. So here is our expectation, right? So now this is a lot more concrete. It's not just some confusing abstract expectation. And we can certainly pull the 1/2 out of our expectation, and we can push our expectation through linearly. So this is 1/2 the expected value of x1 given x1 plus the expected value of x2 given x1. And let's just write an aside here. This point will come up a couple times. If I look at the expected value of some random variable z given itself, what is that? Well, let's back up. What does this notation mean? The expected value of z given z is, let's say, little z. Well, let's just be even simpler. Let's say z is 5. The expected value of z given z is 5. Well, if z is 5, the expected value of z is 5. And we know what z is, so in fact it has no probabilistic distribution really, it's just 5 all the time. And so certainly its expected value is 5. more generally, if I have some, this is a lowercase z, it looks like a 3, it's a script z. Expected value of z given z is some generic little z, right? Generically, it's going to be little z. And so when I look at what I mean by the expected value of z given capital Z, right, all I'm doing is I'm taking this thing and I'm changing little z to be probabilistic z. So the expected value of any random variable given itself is itself. It actually doesn't do anything. So when we come back up here to our expectation, we said this is 1/2. Expected value of x1 given x1 is x1. And the expected value of x2 given x1, x2 is independent of x1, so we actually don't care about that conditional. x2 is independent of x1. So you can drop the conditional expectation. It doesn't actually, knowing x1 or not, won't change it because they're independent. So that's 1/2 x1. Expected value of x2. x2 is normal theta 1, so it's theta. So remember that this is our quantity phi. So let's go back to just recap what we're doing here, right? I had my bad, probably, estimator theta hat. And I wanted to refine it. And I'm going to refine it by conditioning on x1. Notice neither theta hat nor x1 explicitly depend on theta. Theta does not appear in the formulas. Nonetheless, when I condition on x1, phi does depend on theta. And so this thing is not a statistic. And so that kind of refinement move by conditioning on x1, in terms of finding a good estimator, a better estimator, is not actually that helpful, because that refinement step has given me something that is not actually a statistic. It is something that depends on the unknown parameter, and so that's not going to help me estimate that unknown parameter. Nonetheless, the facts I talked about above, these two, didn't depend on phi being a statistic. It's generally true, and it's true in this case too. Notice, however, my claims are true. Expected value of phi is 1/2 the expected value of x1 plus theta, which is 1/2 2 theta is theta, because this thing here is theta. So check 1, phi is unbiased for theta. Remember, phi was refining theta hat was unbiased for theta. Cool. I also had my second claim was that phi should have a lower variance than theta hat. Now let's look at that. Theta hat, the variance was 1/2. What's the variance of this thing? 1/4. The variance of x1. In fact, we don't even need to worry about that theta because that's an additive shift, and that variance doesn't care about that additive shift. So this should be 1/4 the variance of x1, which is 1/4, which is certainly less than 1/2, and 1/2 was our variance of theta hat. So our second point is true, is that this refinement does produce a quantity, not necessarily a statistic, but a quantity that is still unbiased. This phi thing is still unbiased, and its variance is lower. So we're kind of almost there. But what we haven't done correctly is the problem with this is that phi is not a statistic, so we can't actually use it in any useful way. So we want to do is we want to choose our W carefully so that when we play this refinement game, when we refine theta hat into something else, if I choose W carefully, this phi will still be unbiased, have a lower variance, but also be a statistic. And if I can do that, I've just come up with a better estimator. So let's consider a second way of doing this. So let's say, consider instead W to be x bar. And let's redo our calculations. Let's redo calculations. Phi, expected value of theta hat, given w, is the expected value of 1/2 x1 plus x2, given now x bar. Cool. And we can certainly distribute that expectation so the 1/2 comes out. This is 1/2 the expected value of x1 given x bar plus expected value of x2 given x bar. And what I want to notice now is that my x sub n's are IID some distribution. Doesn't even really matter. So the expected value of x1 given x bar is the same thing as the expected value of x2 given x bar. And I can't write bar, right? Because x1 and x2 have the same distribution is the same thing as the expected value of x3 given x bar. They're all the same. They all have the same distribution. Because x bar doesn't privilege one of them over the other. It's kind of, you can permute them and you get the same kind of thing. And they all marginally have the same distribution. So I'm just going to pull some clever moves here, where I could say, instead of x1, the expected value of x1 plus given x bar plus expected value of x2 given x bar, those are the same. There's some number, I don't know what they are, or there's some random variable, I don't know what they are, right? There's something. And I could just say this is twice the expected value of x1 given x bar, because those things will be the same. And so clearly this is just the expected value of x1 given x bar. And even more cleverly, I could say this is 1 over n times n, expected value of x1 given x bar. And I could reverse this and use this fact in reverse. I'm saying it's 1 over n, expected value of x1 given x bar, plus expected value of x1 given x bar, right? Do this n times. All right, so I do that whole thing n times, certainly. And then I could say, well, expected value of, let's say the expected value of x1 given x bar is, leave that, but then for the second one, I know this is the same thing as, I could put x2 in there, that's the same thing, and I know I could, for the third one, I could put in x3, because that's the same, and I could do this with all of them up to x capital N. So it looks like I'm playing games here, but everything here is a valid probabilistic move. And then I'm just going to factor out this expected value, right? So this is 1 over n, expected value. And this would be x1 plus x2 plus n, right? So I can factor it out like that. So that's certainly allowed. And I could even push my 1 over n inside there, right? So I could push that in there like that. This is just playing games so you can recognize what this expected value is, right? All we're trying to do is recognize what this is. So I'm playing games until we get to a point where we recognize what the answer is. Nothing more than that. If you're smarter than me, you might be able to recognize it immediately. But what this is I've just shown, is this expected value of x bar given x bar. And our claim was that the expected value of any random variable given itself is just itself. So what was I even calculating here? I was calculating phi, right? I said phi was this expectation, and I played a bunch of games to convince you of what the answer actually is. but all I was doing was calculating phi, which was a refinement of my silly estimator, which is the average of x1 and x2, and I had refined it given w, which was x bar. And when I do this refinement on this, and this time, I get that that is x bar. So when we had done this, where we had just refined where w was x1, we got something that was okay, but it wasn't actually a statistic, and it's not that useful. When I redid this and we used w as x bar, we got that refinement of our bad estimator, theta hat, gave us something better, x bar. And in fact, we know in this problem, x bar is the best estimator. So we've actually refined this. This refinement step has given us the best estimator. This thing is obviously a statistic. I mean, x bar is the prototypical statistic. And we know our two facts. We don't have to prove these, but we know our two facts are the expected value of phi, which is the expected value of x bar, is certainly theta. All right, so it has the same expected value as theta hat. And two, our expected value, our variance of phi is the variance of x bar, which is 1 over n, because our sigma hat, or our sigma squared is 1, right? All right, recall here that my xn's come from this distribution. So x bar is sigma squared over n, sigma squared is 1. So, okay, 1 over n, and that is certainly less than 1/2, which is a variance of our bad estimator, theta hat. Our kind of naive estimator just using two of the samples. But now, in this case, theta hat is a statistic. I'm sorry, theta hat phi is a statistic. And so this whole procedure, what I'm calling a refinement procedure, by taking theta hat and refining it by conditioning on w, in this case it worked. It gave us something with the same expectation, that's still unbiased, has a lower variance, and is a statistic. And so phi is a better statistic than theta hat. So phi is a, quote, better, same bias, lower variance, statistic / estimator of theta hat, of theta. It's a better estimator in theta. In fact, and we won't show this time, but phi is the UMBUE. So today we're going to talk about, tomorrow, next lecture we'll talk about how to show that is the UMBUE. This lecture we're going to talk about how do we ensure, so what's the difference here, right? How do we ensure that this phi is a statistic? How do we ensure 0.3? Because if we can do that, then we've just come up with a procedure where we can take a bad estimator and refine it into a better estimator. And if we do this cleverly, we will get the UMBUE. Because when we did this the first time, when we, what's the difference in W's here? Oh boy, come on. What's our difference? We did it the first time, our W was x1, didn't work out. We got a phi that wasn't a statistic. Second time, phi is x bar, does work out. We get a phi that is a statistic. And the question is, what's the punchline? When is this going to work? And the answer to that is given to us by the Rao Blackwell theorem. Rao Blackwell theorem named after C.R. Rao, who I believe is still alive. Blackwell is not. Blackwell is actually an interesting character in history. He was the first black tenured professor at Berkeley, and I think the third black person to get a PhD in the United States, certainly a PhD in math. Had a tough life, but a huge name in statistics, just really monumental contributions, including the Rao Blackwell theorem named after him. Him and C.R. Rao. Okay, so what does the theorem say? What's the punchline? what is the difference in these two cases? Why did one of the w's work and the other didn't? Well, turns out it will work if w is a sufficient statistic. So you thought you might have avoided ever talking about sufficient statistics again, but turns out they come back. So let's write out the theorem. Let theta hat be unbiased for tau theta, and w a sufficient statistic for theta. Then if we do this refinement thing where we define phi to the expected value of theta hat given w, and so w is a sufficient statistic for theta, then we get everything we want. 1, phi is unbiased for tau theta. 2, the variance of phi is less than or equal to the variance of theta hat. And 3, phi is a statistic. Doesn't depend on the unknown parameter, i.e. phi is a better estimator for tau theta than theta hat. So this is the Rao. So doing this procedure, creating phi, is called Rao Blackwellization, is what people will call it. So the punchline is basically we need w to be sufficient. If we do this and w is sufficient, if we condition on a sufficient statistic, we refine our estimator. We won't get anything worse. It actually might not make it better, but it definitely won't make it worse. So we can do a proof of this. And that's kind of what we're going to spend. We'll go through. It's actually not so bad. This is a real quick proof because we already proved 1 and 2. Those actually didn't depend on the sufficiency. So let's show 3. Phi, of course, is the expected value of theta hat given w, right? And so what is this expected value here? What is expected value? It's phi of x. You integrate phi of x against the conditional distribution of how do we want to write this? Something like that. So the conditional expectation of phi given w is the expectation of x given y is little y, right? So is what this integral of x times f of x given y dx, right? Or more generally, the expected value of some, let's say function g of x given y is little y would be the integral of gx f of x given bar y dx, right? Oh boy, what did we do? Go back. Dy, right? So this is kind of our aside, right? And this is what we're calculating here. Actually, I made a mistake here. This should be x, right? So the expected value of, right? So recall that theta hat is theta hat of x, and w, we're going to go w of x, right? So you could write this as, if you want to just make it more explicit, theta hat of x, w of x, right? So this theta hat plays a function of g here. So we integrate theta hat of x against the conditional distribution of x, and y, in this case, we're using w, right? Cool. Not so bad. However, W is sufficient for theta, and the definition, sufficiency, how we showed sufficiency was we applied that factorization theorem, right? That was not the definition of sufficiency. The definition of sufficiency is that W is sufficient for theta if the distribution of x given W is free of theta. Right? That's our definition of sufficiency, is that if I condition on my sufficient statistic, that conditional distribution no longer depends on theta. What does this mean? This means that certainly theta hat is free of theta, and f of x, I guess there should be a little tilde there, right? Given W is free of theta. And so the whole integral, nothing in their integral depends on theta. So the whole integral doesn't depend on theta. And so that integral defines phi. So, whoops, not theta. Phi is free of theta. That is, i.e., phi is a statistic. So actually really, really cute, nice little theorem. And all it's doing is abusing that definition of sufficiency. So now you see why we define sufficiency, how we defined it. It helps us here. And the idea is that all this is that f of x given W, if W is sufficient, basically if and only if it's sufficient, that thing is not going to depend on theta, and so the whole thing won't depend on theta, and so phi is our statistic. And parts 1 of 2 of this theorem are already true. Phi is still unbiased for tau theta, and the variance of phi is lower than the variance of theta. So our Rao Blackwellization, by conditioning on a sufficient statistic, you can improve an estimator. So if you ever take an estimator and you condition on a sufficient statistic, you will get a better estimator. And that's the Rao Blackwell theorem. And so it's the kind of first baby step towards getting the UMBUE. We've taken a bad estimator, we've made it better. And if you're clever, which we'll see next time, pretty quickly, that will give us the best estimator possible. So I think we're probably at about time here, and that seems like a good place to stop. So we'll call it here, and that is our first step. Next time we'll talk about the Lehmann-Scheffé theorem and how we can use this to actually get our UMBUEs.